Right? Oh, that was.
Wine
Yeah.
enough and you get cookies and extra credit.
Cookies and extra credit. All right, ready, set. Oh, look, it got recorded. I better go shopping tonight before I forget those cookies. Okay, testing hypotheses about the population mean of paired differences. So first of all, for hypothesis testing for these means, you need to use your T table, right? So if you don't have that out already, you should get that out. If you don't have one, like your irresponsible teacher here, you should get one out of your little box. There you go.
The tables?
Yep, there's our Z tables there too, but keep them separate.
What? Oh, okay.
Some of those are Z's and some of those are T's. I don't have like,
Do they have the same stack?
the one has a paper clip on it.
Alright.
Okay, and if you're looking at your table, notice how it says that a p-value in the table is the area to the right of T. So what that means is you have this T distribution, which is this bell-shaped thing, also with the mean of 0, and you're at the T value. It's finding the probability that your capital T is bigger than or equal to that little t. Unlike the Z table, which goes like from the left down, this goes from the right up. And some people had really good questions over the weekend about, oh my gosh, does the sign matter? What's going on here? When you end up with probability that something like, I don't know, negative 3.2 is less than T, that's like this area. How do you change that to make it the area that you want?
3.2 greater than 2.
Probability that T is, did I do this?
Backwards.
I did it backwards. Wait. I'm so sorry. Dyslexia rules my day today. Probability that T is less than negative 3.2 equals probability that T is greater than positive 3.2. So that's what we were doing with if you got a negative, and this also, the direction of the t-quality inside the parentheses has to do with your null hypothesis. It always goes the same direction. Until then, you maybe flip it around. Okay? So what we're going to talk about today to start is talking about how to test populations of paired differences. And this is really similar to one mean. So remember that paired data is described data that occurs in natural pairs, before, after, stuff like that. What else have we had for paired data? Mother-daughter. I think there also was a husband-wife example, right? Okay. This also could be matched pair design, which participants are paired and then one unit in each pair receives a treatment. There was an example where we paired with age. Does that ring a bell? You said, okay, we're going to do a memory test, and we're going to pair people based on being similar ages, so that the age isn't a factor in this memory experiment. So yeah, before and after weights, after a diet program, or you could also talk about performance on a college entrance exam. Before and after a training program is supposed to help you get better, to prove your program works. Yes? Okay. So those are kind of examples of paired differences things. Okay. So we're going to use a one sample t-test, just like we did for means in the last section. So we call this a paired t-test. Now, if you're talking about differences, you're trying to knock down the hypothesis that your differences are nothing, right? So your null hypothesis will always be the difference is 0. Which means if that difference is 0, there is no difference, right? And your alternative could be one of three things. That your mean is just not 0. That would be a what kind of test? Two-tailed or two-sided. They're both fine. It could be that your mean is bigger than 0. Or what's the other one? Smaller than 0. Okay. So first you summarize your data into an appropriate test statistic after first verifying the data conditions are met. Calculate the differences for each pair if it hasn't been done for you already. Verify that n is large, which is like 30, and if not, you can still do it, just note that your n is small. Compute the sample mean, which they call d bar, and your sample standard deviation, which is called SD. And then the structure of the t statistic is pretty similar to what it was the last time. So last time we had the sample mean minus the null value over the standard error. And just to remind you what that was last time, this was x bar minus mu over
Standard deviation over.
s over root n, right? Okay, so that's for last time. So what's going to change for this stuff? What does x bar become? D bar. What is our mu d always equal to in this case? 0. Over s sub d over root n, but same basic structure, right? Yes. And then you find that p-value using either a table or Excel and decide whether the p is statistically significant. Oh, and just one warning about the p-value. If your test is two-sided and you're using the table, what do?
Double.
Multiply p by 2, because that table only gives you one tail, not two. Right? Remember that? Okay. So tell me if it's statistically significant, is your p small enough, and then make me a conclusion in the context of the situation. All right. So give the value of the test statistic t and the p-value or p-value range for this situation. So the range would allow you to say my p is between these two numbers because I can't find on my table exactly, because this doesn't list them all by far. Okay, so first get the t-value. So t is d bar minus 0 over sd over root n. So what goes in for d bar? Over.
15 over 16.
Great. And when you calculate this, you should get negative 2.07. So please just verify that you can actually get that by punching some buttons in your calculator. Anybody else get that? Okay, so now, is this a two-sided or one-sided test? Two-sided. What are the degrees of freedom? 59. Our table doesn't list that, but 60 is close enough, right? Yeah, okay. So look at the 60 column and then look at the top row. The t-value, we have our t-value is in between 2 and 2.3, right? Does that make sense? Yes? So our p-value is between, what is p on the smallest end? Like what's the, or biggest, either one? 0.025, that would be the biggest it would be, right? How about the smallest? 0.012. Do you guys see that this comes from the column that has 2.33 equal to t? And this is from the t equals 2.00. If it was closer to one of those, which one probably is it closer to? The left or the right? Probably the right one, because this isn't all that far off from 2. Does that make sense? Okay. So, and actually this is not quite right because this is not doubled yet, right? So the range for the two-tailed test is 0.024 less than P less than 0.05.
Could you explain why on that?
Say that one more time.
Could you explain that one more time?
Why it's two-tailed?
Yeah.
Oh, because when I just specify that the mean isn't, the difference isn't 0, it doesn't specify if it's below or above 0.
Okay.
And that means either one's an option.
Okay.
And that's why they've got, this just finds the area in one tail, whereas the not equal to means the area is in both extreme tails.
Okay, all right.
Okay, so if, just as a not actually here, but just in case it were, if you had alpha equal to 0.05 as your like significance threshold level, would you reject H naught or fail to reject H naught? You would reject H naught. Does that make sense why? Because the p-value is at least at that borderline. Yeah, just move it up? Yeah, okay. Is that good enough? Okay. If you're ahead, go ahead and read the next one, and Erin's gonna give me a thumbs up when she's done writing. You good too? Okay. All right. So most people complain that they gain weight during the December holidays. I blame my grandma who keeps putting out chocolate even though I don't really want to eat it. It's all my grandma's fault. So, poor grandma. She can't even defend herself. So this person wanted to determine if that is the case, and they sampled the weight of 195 adults in mid-November and again in early to mid-January. And the mean weight change for the sample was a gain of 0.37 kilograms with a standard deviation of 1.52 kilograms. So what they told us there is that D bar is equal to what? 0.37, which is approximately 3/4 of a pound, right? It's about 2 kilograms per pound. Really, it's 2.2, but close enough. What else did they tell us? S sub D is... Okay, great. So, we want to tell if there actually is weight gain or not, right? Does that make sense? So step 1 that we should label is do the null and alternative hypothesis. So H naught would be that the difference in weights is equal to what? 0, which corresponds to no weight gain, right? Okay, and if we're suspecting weight gain, if they did sort of like January weight minus November weight, and that was gain, that'd be a positive number, right? So
D is greater than 0.
it'd be mu D is bigger than 0 for the alternative. We're not suspecting that they lose weight, we're suspecting that they gain weight. And of course, this would be different if they reverse the order of their subtraction. Does that also make sense? Okay. Okay, so that's step 1. Step 2 is the bulk of the work. Get this test statistic. That is the Z value or the T value. Remember, Z values are proportions, T values correspond to means, right? So T equals D bar minus 0 over S sub D over root N. So, what goes in for D bar? 0.37 over,
1.92.
over,
135.
good. Okay, I got that T was equal to 3.399, or T equals, I guess, 3.4 would be how that would round, wouldn't it? Anybody else get that? Yeah? Okay, great. Is everyone okay with the test statistic thing? You got that? Okay, great. Now let's find the p-value. Now this distribution is not all that different from the z distribution. When you get z values that start to get bigger than like 2 or 3, you start to get things that are significant, right? Same idea here. Does that make sense? Like 3 standard deviations-ish? It's a lot. So step 3 is to get the p-value. So probability that our t is bigger than 3.4. So why did my inequality go that direction?
greater than?
So it was the null hypothesis, right? Okay. So this probability tells us that our p-value, so what's the biggest t-value that's given in our table? 3. And this t-value is even bigger, right? Which means the p-value that we would get would be even smaller. So this is point, yeah, and how many, what's our degrees of freedom?
194.
Okay, and so I'm just gonna use the 100 row because, like, you know, right? So, goodness,
0.002.
002, okay. Okay, if alpha equals 0.01, that's what they told us, right? What doing? Do we reject H naught or fail to reject H naught? Reject H naught. And step 5 is to accept HA. And I'll number these steps in your test so you don't like have to memorize what they are, just how to do them. Does that make sense? Okay, so for 5, just interpret what this means in the context of the situation a little bit. What does it mean to accept HA? What are you saying happens?
If there is weight.
There is weight gain over the holidays.
And for these, you wouldn't say like with 95% confidence or any of that?
Well, you kind of already stated that right there. Does that make sense? Yeah. So weight gain over the holidays is for real. That's what I did. That's my strategy to combat Grandma's cookies. Just in case you're interested in, doing a marathon.
Yeah.
Yeah.
2 miles definitely makes sense.
We did 10K.
For a little bit of weight gain.
Yeah. Actually, I think that there has been no study, I'm not gonna be wrong, but I definitely read a book that claimed that there have not been studies confirming that exercise actually causes weight loss.
Yeah.
As in, like that alone.
Base metabolic rate.
Yeah, and
Based on that alone?
yeah, your basal metabolic rate's kind of anyhow, but the point is that maybe this doesn't actually matter. It matters for other reasons, but maybe not, weight loss is not one of them. Anyhow, so many people have high anxiety about visiting the dentist. Hate the dentist. So painful.
That needle's so big.
Researchers want to know how this affects your blood pressure. So probably if you're more stressed, what happens to your blood pressure? It goes up. So the hypothesis is that people have a higher blood pressure after visiting the dentist. So 10 individuals had their systolic blood pressure measured while they're at the dentist waiting room, and again, an hour after the conclusion of the visit. Oh, an hour later. Okay. So I guess the hypothesis is that the BP is higher before, and then they get it over with and calm down. That's the hypothesis. Okay. So first, what is the parameter of interest?
Dentist patients?
We care about, is it, when they talk about parameter, that means like, is it a proportion? Is it a mean? Is it a mean of differences? What do you think? It's a mean of differences, right? So the mean difference in blood pressure, where we go before minus after a visit. And something we should, I think I left U space in your notes. I just lack space here. Am I right that there's a little bit of space before part A? We should actually compute all those differences. Do you see what I mean? Like, what's 132 minus 118? 14, right? What's 135 minus 137? 149 minus 140? Okay. 133 minus 139? 119, 107, 12, and then 5, 6, 8, okay, 4, and 7. Okay, most of those are positive, right? Okay. Okay, ready to go on to the next slide, or you just need me to? So the idea is that people are calmer after them. This is kind of like a test, right? You've studied for 6 months and you're going to pass and see if you have no cavities or not. That's how I do this test. Okay, what is the null hypothesis? So nothing going on would mean that mu sub d is equal to what? 0. And AHA, that something's going on, hypothesize probably that it's bigger than 0. Because we have an idea that we think that your blood pressure before is higher than your after. That's at least our hypothesis. Okay, so carry out the remaining steps to test the hypothesis. So I just need to tell you that I found that D bar was 5.7, and I found that S sub D, which I found using Excel, using stdev, and then putting in like a list of those numbers with commas between them, was equal to 6.019. If you get a question like this on your homework, use technology to find those things, okay? Like, I mean it. Please don't do, or Google it, find the standard, like, there probably is a standard deviation finder on the internet, okay? You can use that to get the standard deviations and stuff for stuff this big. It's too tedious. So T star, or T bar, T, both of those were wrong. Get my whiteout pen out. Okay, T will equal D bar minus 0 over SD over root N. So what goes in for D bar? Over 6.019 over root 10. That comes out to be, I got 2.99. Woo! Okay, probability that T is bigger than, did anyone else get 2.99? Yeah? Okay. Okay, what are our degrees of freedom here? 9. That one actually is listed, isn't it? And this is pretty close to 3, right? So P is about equal to, or close enough to what number? 0.007. Okay, and then what do you do about this silly old H naught? Reject H naught. Okay. And step 5 is just make a conclusion in context. So blood pressure is what?
Definitely lower after leaving the dentist.
Is lower on average after leaving the dentist. Awesome. So we'll stop there and we'll come back and start 13.4 next time, and we will also start the review next time. So we're going to finish the lesson. Yeah? Anything?
I said 2 weeks, right?
2 weeks after Thanksgiving is approximately when this class is over, yes. I know.
Yay.
It's a bit nuts. So the last hypothesis test we have to talk about is the difference in two population means. So a situation where you care about mean 1 minus mean 2. And after that, we're done with confidence intervals and we'll just do a little bit of, or we're done with hypothesis tests and we'll review a bit. So we want to test whether the means of populations represented by two independent samples, if are actually different. Think like the mean time to get over a cold with the zinc versus no zinc, right? Is the recovery time different or not? Nothing going on means the recovery time is the same, right? A difference means one mean is bigger than the other, right? or just not equal to. So this procedure is called a two-sample t-test or a t-test for the difference in two means. And why would you think it's called a two-sample t-test? There's means for two groups, does that make sense? As opposed to paired differences, which means it's really just one group with two measurements per person. Does that make sense? Okay. So in each of the following situations, determine whether the alternative hypothesis was HA mu1 is bigger than mu2, less than mu2, or not equal to mu2. Okay, so this isn't a spectacularly awesome question, I'm sorry. When you're testing for a difference in population means, does it make sense that H naught is always that mu1 minus mu2 equals 0? Because nothing going on means the means are equal, right?
Yeah.
Okay. Okay, and they have a p-value of 0.024. Okay, so now this thing, you have two options for H, well, three options for HA. Either the difference in your means is positive, the difference in your means is negative, or there's no difference at all. So now, one thing that's true is that if this difference in means is positive, that corresponds to a positive t-value. Does that make sense? If your means and difference are negative, which means mu1 is less than mu2, that's going to be a negative t-value. And this guy could go either way. So I think since this is a negative value, it's either mu1 minus mu2 is less than 0, or HA is mu1 minus mu2 is not equal to 0.
And you figure that out by the t-value, correct?
Yeah, by the t-value. Although part B is going to be the opposite. I don't like this question. You know what I say?
Scratch it.
Scratch it. And if there's a question that goes in your homework, I'll just remove it because I can look really quick and just take it off because it's silly. We're moving on. Not helpful. Okay, so first thing we need to know. Ignoring that last thing, we'll delete that slide. So tell me if this is, because one thing you have to distinguish for sure is, do you have paired differences or do you just have two separate populations, right? So is this a paired t-test, meaning you have paired data, or is it a two-sample t-test, meaning you have two different groups? So you have 15 marathon runners, and you took their weights before and after a training run to test whether they lose dangerous levels of fluids during a run. Paired. So for each runner, we have two measurements. Okay. Random samples of 200 new freshmen and 200 new transfer students at a university were given a 50-question test on current events to test whether the level of knowledge differs for new freshmen and transfer students. What do you think? Two different samples, yep, so this is a two-sample. Because we have two separate groups. Everybody's so nice today, thankful.
We're here for the extra credit.
I know, I don't doubt that you're not,
I was playing a
I
couple
don't doubt that it's your, like, just that class because I'm super funny and, yeah, no, I know, I understand. That too, yeah, that's what I thought. Okay.
For my 15 minutes of laughs a day.
Exactly, because I'm so hilarious. Now, one thing that happens with these paired means is you could have a situation where you, remember we did this whole, with the confidence interval, we also did this thing with the pooled standard error. Does that make it ring a bell?
Yeah.
So you can do either one of these cases. So the unpooled case, this is your standard error, which we already know that formula, right? That's not different. If the standard deviations are equal, oh, and in this case, How do you find the degrees of freedom?
N1 plus.
It's the, nope, this is the smallest of N1, N2 minus 1, okay? So for that first case, in that unpooled situation, you look at the N1 and N2 and say, who's the smallest? And then you do one less than that smallest number, okay? If you do a pooled sample, you should only do this if the standard deviations are equal, which the standard deviations in your sample are never going to be exactly equal, right? But if they're about the same, then you could pool them together. And an advantage of pooling them together is that the degrees of freedom is now,
N1
Plus
plus N2 minus 2.
yeah, minus 2 this time, minus 1 for each of them. And remember that bigger degrees of freedom, that shrinks your T star, right? Which makes your interval narrow. So bigger DF implies smaller T star, which leads to narrower interval. In general, if I want you to use a pooled test, I will ask for it explicitly. Otherwise, you can use the unpooled one. Like, I'll be really clear about do this or don't do this. That says narrower. It's just written kind of badly. Okay. So let's do an example of hypothesis test. I think one will do it. So in a study, sedentary men were randomly assigned to be placed on a diet or exercise for a year to lose weight. 42 men were placed on a diet, so that's our N1. And the remaining 47 were put on an exercise routine. The group on a diet lost an average of 7.2 kilograms with a standard deviation of 3.7. The men who exercised lost an average of 4 kilograms with a standard deviation of 3.9. Okay. So do you agree that N1 is 42?
Yes.
What's the X1 bar?
7.2.
Uh-huh. What's the S1, standard deviation? 3.7. Great. What's N2?
47.
Mm-hmm. X2 bar?
4.0.
4.0, yep. And standard deviation for that sample was
3.0.
3.9. Spectacular. Do you guys all agree with that? Okay. So state and test appropriate null and alternative hypotheses to determine whether the mean weight loss will be different under the two routines for the population of men similar to those in this study. Specify what the value of alpha you choose to use. Okay, now one question before we start. We're going to use the unpooled procedure, but could we use pooled? Yeah.
Yeah.
And what would be the reason that you think pooled is appropriate? Or may pool?
Deviations are extremely close.
Mm-hmm. Pooled would be okay since S1 is about equal to S2, right? That would give you a reason that that's all right. But we're going to do unpooled, so I didn't specify. Okay. So step number 1 is to do the hypotheses. Okay, so in words, what's the hypothesis going to be?
That men who go on a diet lose the same amount of weight as those who exercise.
Yeah, men who diet lose the same amount of weight as men who exercise. Okay, so that would be mu1 equals mu2, or mu1 minus mu2 equals 0. And what's HA? Did we specify that we think 1 is better in any place? I think not obviously so. Does that make sense? Like, we were trying to show that diet is better or vice versa, right? So men who diet lose a different amount of weight than those who exercise. So mu1 not equal to mu2, or mu1 minus mu2 equals 0.
Would it be does not equal?
Yes, it would be does not equal 0. I was just seeing if you got into a cookie coma. Okay, step number 2 is to find your test statistic. This is where the bulk of the work is, and it's either a Z or a T, and you have to know which. So in the case of means, it's T, right? When is it a Z? Proportions. Okay, so T equals, so it'll be X bar minus your null value over standard error of X bar. Oh, in this case, I'm so sorry, I boo-booed a little bit. It isn't just X bar, what should it be?
Standard error of null value, right?
No, that's for proportions. That's why we have to actually use T's in this case. Yeah, it should have been X bar 1 minus X bar 2. And then this is standard error of X1 bar minus X2. It's standard error of the null value if you have a proportion.
Okay.
That's the difference. And it's because that if you wanted to find the standard error of the null value, you have to know sigma, which is the population standard deviation, and you don't know that. What goes on for your null value in this case? 0. Does that make sense? Because mu1 minus mu2 is 0. Okay, so first let's find the standard error of x1 bar minus x2 bar. Do you remember the formula for that?
S1 squared over N1. S2 squared.
N1 is 2 squared over N2. Okay. So S1 was 3.7, right? Over 42. 3.9 squared over 47. I get that this is about 0.806. What goes in for x1 bar?
7.2.
Minus 4.0 minus 0 over 0.806. What do you get for t? I got 3.97 as well. Anybody else get that? Okay. So there's your test statistic.
Another question.
Yes.
Beginning of the equation, when it says x bar 1 minus x bar 2 minus the null over s e of x bar 1 minus x bar 2. In the z statistic, is it flipped?
In the Z statistic, I think someone else asked us a good question. This is standard error of your null value. That's what you're thinking, right? Yeah, so this is the case if it is a Z statistic. And that has to do with the standard deviation, the standard error formula. Using, in this case, it uses sigma over root n. We don't know sigma. There's no guess for what the null value is for the standard deviation. That's the difference. But you're right that with the other situation, it's null value. Okay. So step 3 is to get your p-value. Is this a one-sided or two-sided test? Two-sided. And degrees of freedom is equal to 41, do you believe? Which is closest to 40, which is the closest thing on our table. Okay, so the probability that our t p-value is bigger than 3.97. Yeah, so what's the biggest t-value that we have? 3, right? So if you go down to the 40 row, your p-value is smaller than what number? Less than 0.002. So your p-value is less than so your actual p-value is less than 0.004. Does that make sense? So you must double as we have a two-sided.
I did it too.
What'd you do?
Saw you make the mistake.
Oh,
Did it.
you also spelled wrong? Yeah, I'm so sorry. My spelling mistakes
I
here.
didn't even look at it, I just heard you say it.
And steps 4 and 5 can be combined. Make a conclusion. And interpret. Ugh. It's just gonna be gross. Okay, with the conclusion, do you reject H naught or fail to reject H naught? Reject H naught.
Did it say what?
Significance.
Specify the value.
Let's use alpha equals 0.05. That's the sort of standard. Okay, reject H naught and you accept HA. So what does that mean in this context?
That men who diet lose a different amount of weight than men who exercise.
Men who diet lose a different amount of weight than those who exercise. Yep. Okay, and I think we kind of already did part B, didn't we? It says explain how you decided to use a pooled or unpooled. I mean, we could have used pooled, and maybe it would have even been better. Yes, the first standard deviation is pretty close to the second. One thing to be careful about, this was something that happened on your quiz. If you fail to reject H naught, this does not mean H naught is true. Does that idea make sense? I think we said that before, right? Think about H naught is that your
There's not enough evidence to support.
there's just not enough, yeah, what you really have at this point in time is there's not enough evidence to reject H naught in favor of HA. So you just don't know. Because one easy way to not reject H naught is if your sample size isn't big enough. Does that make sense? You get a p-value that's big because your sample is kind of small. That happens. So you just don't have enough evidence. And it could mean that H naught is actually true. It could just mean that you just don't know. There's just not enough evidence to see the effect. So you never get to accept H naught.